Let's see, did you come up with the problem you wanted to look at?
Oh, it wasn't like a problem, it was more of just a general format of like when it's any integral of, just say like 2x
I'd like to.
y to the cubed plus 3y squared x squared dy. And the integral, the bottom bound is the coordinate point 2, -2. And the top one is -1, 0. And like my main, oh, and after that y cubed, there's a dx.
Okay, yes.
So like my main question was, could that just be rewritten as like, instead of dx, just putting an I there, and instead of like the I hot, like the I hat, and then the dy just a j direction, like a j vector?
Yeah, one of the hardest things in this section is the notation.
It's like, that's how I
Is there a
treated it.
parametric curve given with this? Or is it just these 2 points? If it's just those 2 points, then I assume it must be for a conservative force.
It was show that the integral is independent of the path.
Yeah, so it's
and then-
conservative, then, yeah.
Yeah, then use,
When they put the 2 points, that's because it's a conservative field that you're moving in. And it doesn't matter what path you take, so they just put the endpoints. So they add this to all those other notations we wrote last time. But this means the same as if you have f equals the vector, well, you wanted the ij notation, 2xy cubed I plus 3y squared x squared j. With that f, this is integral along the curve f dot dr, where which curve you pick doesn't matter as long as you go from this point to this point with a piecewise smooth path. So you can also write it in this way, which would be, let's say it's that. So you can think of it as this vector field integrated along any curve you want between these 2 points. Now, the way to evaluate it normally is to say, oh, this is the integral from a to b of 2xy cubed dx dt plus 3y squared x squared dy dt. This will work on any path, any piecewise smooth path you take from this point to this point. This will work. You can do it that way. So maybe the easiest thing is take a straight line, right? Just make a parametric curve. But you know what's a lot easier than making a parametric curve even and doing this? You'd have to find out what A and B is according to the parameterization. An easier way is to say that because this is conservative, and you can test it's conservative, right? If you call this F, this little F, and this little G, you notice that the GDX is, let's see, 6 y squared x is the same as this one is df dy, right? Because dgdx equals df dy, this is conservative, and all you have to do is find the potential. That's what they're asking you to do, is find the potential. And it's integral of f, little f, with respect to x. And it's also integral of little g with respect to y. So that this f is its gradient. So there will be a function that fits that because we already checked, right? If I integrate this with respect to x, treating y as a constant, I get x squared y cubed plus an arbitrary function of y is the constant. If I integrate this one partial integral with respect to x, I get, let's see, y cubed x squared, the same thing, plus an arbitrary function of x. In order for these to match up, when this part matches, these two both need to be a constant. So the only potentials that work are phi of xy equal x squared y cubed plus a constant. For convenience, let's take c equals 0. You can take any constant you want because it'll drop out. And you say that this integral for this is just t at the final point minus 1, 0 minus b at the initial point, 2, -2. So this is an example. And if you have a c, there would be a c here and a minus c here, it would cancel. So let's just use phi equal x squared y cubed. This is -1 squared times 0 cubed minus 2 squared times -2 cubed. 0 minus a minus is plus 2 to the 5th is 32. So this one apparently comes out to be 32. So that's what you can do. But it's real frustrating like that. This is a vector line integral. Whenever you see any of these notations, integral f dot dr, see integral f dot t ds. This is popular when you're doing circulation and fluid mechanics, this notation. This one's popular when you're doing work in physics. Or if you see integral f of x y dx plus g of x y y. See, that's another thing for the line integral. And when it's conservative, this book likes to put x0, y0, x1, y1, f of xy plus g of xy. And this just means this, but it shows that the path is path independent. You can take whatever path you want between these.
When it says like show that the line is independent, what part of this, like all that work you just did, what specifically shows that?
Oh, if it's conservative, then it's path independent.
Okay.
That was the theorem. So to check it's conservative, you can check that dx equals gf dy. That'll show that it's path independent. Or you can find phi. If you can do the two integrals, that shows that it's conservative and therefore path independent. You can find phi and show that you match, or check this one. Conservative. Well, it's getting harder and harder. I don't mean that the material is so incredibly intensely deep, but there's just, it's getting complicated, more and more complicated, as you know. More dimensions and more longer theorems and all that kind of stuff. It's complicated, and it's not difficult to understand, really. I turn the projector over here to the next thing. Yeah, thank you for the question. Any other questions? I think we'll learn more if you ask questions like that at the beginning. All right, then I'm going to start talking. You'll probably all go to sleep. Here's what we were doing last time, Green's theorem. One way to evaluate the line integral, right? We said was to rewrite f dot dr as f dot dr et dt and integrate from a to b, right? That was the main theorem that we did for all line integrals. Then we said in a special case that f is conservative, we could take phi at the end point minus phi at the beginning point and evaluate it. And then finally, there's this third case. If you happen to have this nice case where f is continuous with continuous first partial derivatives on a simply connected open region, basically what you want though is a simple closed piecewise smooth curve bounding a region. If you go around a closed curve, and this circle means you're going around a closed curve, what it means. Sometimes they'll put an arrow to show whether it's counterclockwise or clockwise. This has to be counterclockwise. This again is the line integral there. I put F1 and F2 instead of little f and little g like the book does. I like this notation better when I wrote the notes up some time ago. I'm sorry the notes slightly differ. You got little f and little g in the book and F1 and F2 in my notation. Vector field F. To evaluate f dot dr, this line integral, you can take the double integral over the enclosed region by this simple smooth piecewise closed curve of df2 dx, dt dx minus df dy. Now, can you see why we don't use this for conservative forces? Why don't we use this for conservative forces? Conservative force is dg dx equals df dy. So it's just the integral of 0 and you get 0, right? So if it's a conservative force around a closed path, remember that was one of our corollaries, the integral of a closed curve around a closed curve of a conservative force is always 0 because it's phi of the final point minus phi of the end point, but they're the same, right? Final point minus initial point, but they're the same around a closed curve. So you don't use this on those because you already know the line integral is 0. For a non-conservative force, this can be useful, right? And you say, wait a minute, it takes a single integral right to the double integral. How can that be easier? But what we mentioned last time is if this region here is a rectangle or a circle or a rectangle or a disk or something, then that may be easier to integrate over that region than to integrate along the curve along the boundary. Like the rectangle, you might have to break up into 4 pieces here. Now you just got one rectangular region to integrate a double integral. So sometimes this is easier. Engineers use this formula a bunch. For example, when they have closed curves. So that was Green's theorem, and I wanted to extend that a little bit this time. And work through this first example here. This is out of the notes that I put online there. These are my own notes. Tell me what's wrong with these so I can make them better. You're not responsible for this proof. I just thought you might want to see how it came. Let's do this example. Suppose I want to use Green's theorem to evaluate the integral around the closed path of y dx minus dx dy. This again is the vector line integral, just written in this other form. This is the vector field with components y minus x, integral f dot dr is the other notation. It's the same thing. And suppose C, the closed path, is the unit circle at the origin traversed clockwise. Oh, wait a minute. What if it's clockwise? Green's theorem only applies to counterclockwise curves. What do we do? Well, remember on the scalar line integral, the integral along the path doesn't matter which way you go, it's the same value. But on the vector line integral, if you go the opposite direction, you get minus the line integral because the tangent vector points the opposite direction. So integral that we want, integral along C around the closed path, y dx minus x dy, is actually equal to minus the integral along minus C. So minus C means traverse C in the opposite direction. That's notation. And then I'll take minus y dx plus x dy. So I take minus the integral along the opposite direction, and that's the same value. Now I've got it. How do I integrate along minus C, the unit circle counterclockwise now? C was clockwise. Minus y dx plus x dy. Well, Green's theorem says I can do this by df2 dx, so it's dx dx minus df1 dy, or dg dx minus df dy in the book's notation. So it's dx dx minus d minus y dy. Oh, this is just 1, and this is minus the minus 1 is 1. So I'm just integrating 2 over the unit circle. What's the integral of 2 over the unit circle? Pull the 2 out, and you've got the double integral dA over the unit circle. Well, what is the double integral dA over the unit circle? Yeah, it's the area. You take the double integral of 1, it's the area. So it's twice the area of the unit circle, which is pi r squared, pi times 1 squared. So this is just 2 pi. Green's theorem actually made this thing easier, right? You just had to do 2 times the area of a circle. So once in a while, that kind of thing comes up. There's a nice example for it. Comments or questions? All right, maybe I should have written that out on the board. So I'll write it out on the board too. Okay, yeah. Sometimes that's too fast on the overhead.
But these Green theorems assumed clockwise?
They assume counterclockwise.
Assume.
Yeah, yeah. It's like angles always go counterclockwise.
Can you move the camera, please?
Minus the result. All right, so let's move this thing back. Here's my Green's theorem example then. Given the unit circle clockwise. Evaluate integral around the closed curve C. You don't have to put this circle on here because it's closed. It's just convenient to remind people. Y dx minus x dy. That's minus the integral around the closed curve minus c going counterclockwise. Y dx minus x dy. I'll write it a little bit different than I did. Put the minus inside on that. And now if I just take minus this whole thing, it'll give me the same result. So if I call this f or f1, I guess let's follow the book. Little f, little g, Green's theorem. I only went to school for a year until I finally got a degree in college. You have dg dx minus df dy integrate over the region it encloses. Here's R, the region it encloses is the unit disk. Now we take the double integral over the unit disk R of dg dx minus df dy is Green's theorem. Okay. But dg dx is just derivative minus x with respect to x is minus 1. df dy plus 1, and so this is minus 1 is okay. I can cancel these minuses and bring it out as twice the double integral of r dA, which is twice the area of the unit circle. Oh, it's pi, right? So it's 2 pi. There's a Green's theorem example, that one. This is your rotational field, if I remember y minus x. I'll go right there. Sure this thing's turned up on. All right, I'm going to move it to the theorem. I'm going to do a little more than the book does here. I think these are actually important points. They occur in some other books. It's not that they're not in here. It's just they're sometimes hidden in the problem set and so forth. They're kind of giving you a milk introduction, a baby introduction to the stuff, and then they leave the other harder stuff in the back for you to start to decide where to put it in. Here's another theorem, Green's theorem for flux. So let's see if I can do this one. Well, let's put it on the screen. Green's theorem for flux, which is not integral f dot t ds, but integral f dot n ds, where n is the unit normal. So that's called flux. This is if f is a velocity field, then f dot n is the component of velocity flowing out through the curve. See, I'll draw a picture over there. And that's they call flux. So before we said if it's f dot TDS, that's the, I'm going to get the circulation around the curve. F dot NDS is the flux, the fluid flowing out. If you have this kind of a thing, which sometimes you have to calculate, this is a vector line integral, but for flux instead of for work. Is the double integral of the divergence of f. Remember we did divergence in section 16.1. I said, well, eventually we'll get back to it. Here it is. Comes up in one of these theorems here. It'll come up again in a later theorem that generalizes this. Or more dimension, extends this, I guess I should say, to more dimensions. So there it is. And again, the same thing. F has to be continuous, and with continuous parcels on a simply connected open region in the plane. Whose boundary is a piecewise simple, smooth, closed curve, counterclockwise, right? Everything's counterclockwise. Let's try that one. I'll give the big write up there, and you can look in the notes. It's on that E2L that I call the integration. Now, Green's theorem for flux. That can denote the unit normal to C. Given parametrically by R of T, T going from A to B. A nice curve Satisfies all that other stuff. Piecewise smooth, simple closed curve. Nice curve. That's what everybody deals with. See the theorem. Then the integral f dot n ds along C, closed curve. At least put that closed curve. And simple. One of that's piecewise smooth. Counterclockwise. Something matter. This is why you take your math class, right? If you do it in physics, you never know when it works or how it works. You do it clockwise and the thing has pretty bumps in it, and infinite number of bumps and it doesn't work. Why doesn't it work? That's why you have all this stuff. Then this one can be evaluated by taking the double integral over the region of the divergence of the field. Yeah. Where recall the divergence, but it's been a while since then, is actually really easy. So F is just del dot F. Hence, I use a little F and G to match the book instead of my notes. So the book says little f and little g. Sorry for my notes. Just have to translate them. With that being the case, then this is f dx plus dt dy. That's all the divergence is. And here's the geometric concept. You have some curve in the plane, counterclockwise. If there's a velocity field here, F, so this is your sketch vector field F. F dot n is what? It's equal to length of F, length of n, cosine of the angle between them, right? By the dot product theorem. But n has length 1, so it's just length of F, cosine of the angle to the normal vector. So if you have this kind of a situation, here's F, this vector. Normal vector is this one. There's a unit normal. N is the unit normal. Did I write that? Yeah. Then you're taking the component of F in that direction. Let's put F. And so F dot n is this length here, the projection onto n. This is and is that length, not the vector, the length. And what you're doing is integrating the length of that flow outwards around the path, seeing how much fluid is flowing out through the curve, C. All right, so that's Green's theorem for flux. Evaluated by double integral of the divergence. So let's try a problem with that, just to do one of those. The last integral was for the, we have the difference here. I have to move the camera. Or not an Englishman. On the other hand, been doing so far, if we take, again, a closed curve C, and we make F a velocity field like before, speed of fluid flowing on the water, whatever. Vector field. If we take the line integral along C around the closed path, taking counterclockwise again, F dot TDS, F dot NDS, also known as integral along C F dot dr was the other notation for the same thing, right? What is that computing? Now you're taking tangent vector. Let's use this one. Unit tangent vector to see when we're going around this way. So the unit tangent is like that. And you're taking the projection of the F here on the T. So now you're this line. This is F dot T. Projection F onto the direction T, because after all, F dot T length of T, cosine of the angle between them, so it's a different theta. It's the angle between the tangent vector and F, which is this one actually. And so this is actually negative in this case since it's going against that. But T has length 1, so it's length of F, cosine of the angle between them, is the component tangent to the curve instead of the component normal to the curve. So what you're evaluating here is called the circulation because it's the tendency of F to push you along the curve. So this one is called circulation. When F is the velocity field again. The other one was flux, this one is circulation. Take the component thick of the curve, you can calculate flux as you integrate around the curve. And you take the component tangent to the curve, you're computing circulation, they say. This is what the definition of circulation is. So now we observe we're doing something a little different in the value. Green's theorem for flux. Hope that answers the question better about what does the circle mean. It just means going around a closed path, but it might be flux and it might be circulation. And you can also do a circle in higher dimensions when you go through surfaces. All right, so now let's try this example here. Let's consider the circle of radius 2. Oh, all right. All right. All right. So suppose I consider C, that's the curve x equals 2 cosine t, y equals 2 sine t, t running from 0 to 2 pi, once around the circle of radius 2. Oh, boy, I'm sorry, I did minus pi to pi. And then it's the same circulation because you're just integrating the component all the way around one. The same flux, I mean. F is equal to 2xi plus 2yj. And just to give you a hint, in the notes, I use this notation, 2x(E1) plus 2y(E2). E1 and E2 take the place of I and J. These vectors are also called elementary vectors, and unit vectors in the direction of the axes are often given this notation. This is more convenient what the book uses like in the Euclidean plane, but if you get where the axes aren't oriented the same direction and so forth, they're going to switch to this. I use those, but anyway, so this is the other notation for this. All right, and then evaluate flux, the fluid flowing through the boundary there. Curve. Interval F dot NDS. How can we evaluate that? We could compute the unit normal, right, and take the dot product and parameterize the path and do all that work, right? Nothing wrong with that, except it takes a long time. Or we could use Green's theorem for flux, right? It says, oh, all I have to do is do the double integral over the region, which is really simple because it's a circle, right? Or the region is the disk enclosed by the circle. Mathematics, I have to be real picky, actually, technically. You ever heard that famous group at Orbakey? Something like that. They make sure everything's rigorous and distinction between the circle and the disk and all these. You know, those are important actually, but you just hate to spend your time on it. All right. So this is equal to the divergence of F, which is the double integral of the F by this prescription, this parametric curve is that F, R is the vector with those components, 2 cosine T, 2 sine T. These are equivalent. This is the parametric equations. This is the vector parametric form for the same curve. So we have the divergence is df dx, so it's d2 cosine T. Oops. Yeah. The derivative of 2. This is df dx plus dg dy, that's the divergence. dA around the region. Well, df dx evidently is 2. 2x with respect to x. And dg dy is 2. Oh, what an easy integral. Once again, I have the double integral over the region, just a constant. So this is 4 times double integral. But the integral 1 again is the area of this circle. This circle of radius 2 has area pi times 2 squared, right? Pi r squared. Evidently, this comes out to just be 16 pi. That would be the area of fluid per unit time flowing to the boundary. 16 pi over square meters of fluid surface flowing onto it.
Say that one more time.
It's the rate at which the fluid flows through the boundary C per unit time. This is a 2-dimensional problem. It's the rate of area per unit time. We're going to do a 3-dimensional flux later, then it'll be the volume per unit.
Can you write the equations for like the unit normal and like the capital T?
Yeah, yeah. Oh, yeah, those are exactly what we use, what are in here. You can compute that and compute the line integral directly with the f dot dr dt dt, or you can do it this way to shorten it.
Like can you like write on the board what n equals?
Oh, yeah.
Like that just by itself. Or...
Yeah. Oh, yeah, this should be pointed out, I suppose. R is supposed to be the right normal. That in here, I was just looking for it. So. So this is where you have to help me fix my notes here. think it goes further back is the trouble.
The length of the dr dt right there. Or dr.
It's implicit in this part here in the proof, if you see over there, but and unit tangent vector t is well, let's say given a curve C, we say r prime of t is the tangent vector. It has components x prime of t, y prime of t. Then the unit tangent is x prime of t, y prime of t divided by its length, divided by square root x prime of t squared, y prime of t squared. It's the unit tangent. N is just use little n because I'm using big N for it. It's just minus the way I wrote it. I put dy dt and minus dx dt, right normal. Y prime of t minus x prime of t. You notice this is perpendicular to the tangent, right? This times this is y prime x prime, plus this times this is minus y prime x prime is 0. So this is perpendicular to this by orthogonal, right? This times this plus this times this is 0. And it's divided by the root sum square of these things, which is the same as this one. It's x prime squared plus y prime squared is the unit normal. Unit prime. So as you're moving along the path, C, tangent vector points like this. Right in the normal. So you can evaluate it directly using this for the normal. Oh, and it's in the proof there, but I just need to spell that out. Or you can apply Green's theorem for flux. All right. Here's a real fun one for the mathematicians. I think this just blew my mind when I saw this. It's always, probably didn't hear my talk at the FAA. It's no fun talk this year, but strange, exotic measures of distance and lines and spheres and other dimensions. This is one of those kind of fun problems, kind of. Let me turn this over. See it. One implication of Green's theorem is that you can evaluate the area of a plane region by doing a line integral along its boundary. How about that? We think you integrate along the boundary and get the area flux. Well, that's exactly what it implies. Under the hypotheses of Green's theorem, nice, that we call the area of the region R enclosed by a curve C is one way to evaluate is take the line integral around the path of x dy. That evaluates the area enclosed if you just integrate x dy. Or you can take the integral minus y dx around the curve. Or you can take 1/2 of this one, 1/2 of this one, or 3/4 of this one, 1/4 of this one, anything you like. Combination of these. And the proof isn't actually too bad. Maybe I'll just do it up here though, because I don't think it's important for class. You can look at it in the notes. The area we know is the double integral dA, right? And so now, if we write 1 as dx minus derivative of 0 with respect to y, this is also equal to 1. So this is the same integral, right? It's integral of 1 dA. But now this, if I take this as g and this is f, this is g dx minus df dy for the vector field f with component 0, x. Right? But the component 0x is a line integral of 0 dx plus x dy. Oh, it's just the integral x dy. So that's the proof. And then similar, if you choose d0 dx and derivative minus y with respect to y minus, that also is 1. And then f is minus y and g is 0. So you get integral minus y dx plus 0 dy. Also gives you this line integral. So these two line integrals, either one of them can be used to calculate the area closed. Right? Kind of a fun geometric result. Ah. So the next application is we just field to there. Under the hypotheses of Green's theorem. The hypotheses of Green. The area enclosed, being enclosed, can be evaluated as A equals integral x dy, or area A equals minus the integral. Counterclockwise, you're going to get minus the area y dx, or some linear combination of the two. A is 1/2 this one plus 1/2 the other one. Lots of other things. So here's a simple example down below. Find a formula for the area of an ellipse. This is one of my favorite problems to do with this. What is the area of a generic ellipse in standard position? This equation for the ellipse, x squared over a squared plus y squared over b squared. How do we find that area? Well, we can parameterize the ellipse, recall, by letting x equal a cosine t, I equals b sine t. Does that look familiar? We can, so why that's a parameterization if you want. Does that look familiar? For an ellipse. Because, let's put because, apparently it's not familiar. Nobody wants to say it's not familiar. Right? If I take x squared over a squared, all right, what is that? That's a and y squared over b squared. X squared over a squared is cosine squared, right? Y squared over b squared is sine squared. That's just 1. So all these points are on the ellipse. X squared over a squared plus y squared over b squared equals 1. That's the main thrust of it. It doesn't show that it goes all the way around as t goes from 0 to 2 pi, but in fact it does. But that's the way you can parameterize an ellipse nicely. A cosine t and b sine t. Now, once I have a parameterization, I can evaluate by theorem here. Call it 1. So by 1, the area of the ellipse is integral x dy. Let's just use that form. That's x. Well, x is a cosine t. Oh, let's write out the evaluation formula. We have x, f dx plus g dy. How do you evaluate those? You rewrite it as the integral from a to b of x of t dy dt, right? You just replace the differentials with times dt. And so this is the integral. Let's see, we go from 0 to 2 pi. I should have put it on here. T has to go from 0 to 2 pi. T is no longer the polar angle except when you're pointing in the direction of an axis, but it still goes around once. And x of t was cosine t. Y of t, a cosine t. So y of t was b sine t, so its derivative is minus b cosine t. and then dt. All I have to do is evaluate this integral from 0 to 2 pi. X, and here's y prime. All this is AB integral from 0 to 2 pi. Cosine squared t dt. How can I evaluate cosine squared? Everybody remembers this one, right? Yeah, there you go. Somebody took my class last semester. Yeah, easiest way is half angle. There's also a reduction formula and so forth. But yeah, that's why it is a half angle formula. Cosine squared is 1 plus cosine 2t. When, let's see. Just following the half angle formula, I have cosine t is plus or minus square root of 1 plus cosine 2t over 2. And the cosine squared, the plus and minus goes away, and you get. So half angle formula with instead of half t, you put the t in 2t. All right, so it's that one, and so we get AB. This goes from 0 to 2 pi. Times 1/2 t plus 1/4 sine 2t. 1/2 cosine 2t. Plug in 0 and 2 pi. And 1 falls out because sine is 0 at those points. And I just get AB times 1/2 2 pi. It's just pi AB. Now you see the circle formula, pi r squared is just the special case of the ellipse formula when A equals B, right? A squared would be the circle over A. So it allows you to do some areas in a nice way. Too long in this section. Finally, we have Green's theorem for multiply connected regions. I didn't like the book's homework problems on these, but the engineers run into, electronics engineers, I think, run into these kinds of things. This is out of the notes. Suppose if instead of putting a line integral around a simple closed piecewise smooth curve, you have this union of integrals around the outside and then these around the inside. And the inside one's supposed to clockwise and the outside one is counterclockwise. And maybe there's n circles in here, so it's multiply connected region. Holes inside. You can actually still apply Green's theorem, believe it or not. It looks like this. What you do for the proof. So I think if you see the proof, you remember why this works. So since Green's theorem still works, you call it Green's theorem for multiply connected region. What you do is you break this up into a curve like this that satisfies Green's theorem, right? This is a simple closed piecewise smooth curve here. And another one here. And then you notice that the line integral on here, and these go opposite way, they're minus each other, they cancel. Similarly, these cancel each other, these cancel each other. And so what some of these two line integrals around here, with these canceling, is equivalent to the line integral on the outside counterclockwise plus these clockwise on the inside. And so Green's theorem applies to this top region and the bottom region, which is the same as the line integral over the that I just showed above without these lines. What that says is you can do the multiply connected region by thinking there's two of these Green's theorem style regions and apply Green's theorem to that, and it says put it up there. under the hypothesis of Green's theorem, the integral along C, where C is the union of a counterclockwise outside curve and all these clockwise inside curves, f dot dr, or this notation, doesn't matter, is the Green's theorem result. The integral over the region that's between them, df2 dg dx minus df dy. You apply Green's theorem to these multiply connected regions, outside being counterclockwise, inside being clockwise. If they're all counterclockwise, you can fix this. Not hard to fix it for that. This is just easier to remember. So let's try that for an example then. Gotta get on to the next section here. But there's the statement of the theorem there. Line integral. Some of these line integrals around all the little loops. Some clockwise is minus df. Here's the example. What I want to evaluate the word for the circulation, integral dx plus t, where f is one minus xi plus 3x minus yj. And this is around a closed curve. Actually, let's say C, it's multiply connected. This sum of the figure down below. 2 squares. One to 2, 6 to 7, 1 to 2, 5 to 6. They make like a picture frame here. Inside rectangle, outside rectangle, framing it. This is your region R. Closed. The outside one going counterclockwise, and the inside one going clockwise according to Green's theorem for multiply connected region. So this is just Green's theorem for multiply R. This one. Well, Green's theorem says this. That line integral along C, where C, if you call this one C1, call this one C2. C is the union of C1 and C2. If I take the line integral along C of f dx plus t dy, it's the same there. It's the same conclusion that Green's theorem before. It's just the double integral over the region enclosed between them now. dg dx minus df dy. Same conclusion of the theorem. Green's theorem for multiply connected region. C is the union of these counterclockwise and outside, clockwise and outside. Well, what is that? That's just the integral of the picture frame. R. Let's say dg dx. G is 3x minus y, so its partial with respect to x is 3. df dy, partial with respect to y is 1. dA. Oh, this is just double integral. It worked for me. So double integral of 2 dA was twice the area suppose it's twice the area of the picture frame. Well, what's the area of the picture frame? It's length times width minus length times width on the inside. So it says 2 times outside rectangle is, let's see, 6 by 5. Minus the inside rectangle is 4 by 3. So it's twice 30 minus 12, 18. Times 2 is 36. So this could be the circulation outside, and that's the circulation on the inside. All right, so there's Green's theorem for that picture frame. That's a lot of stuff, and I thought it's complicated. But now you guys got all the things that go with the territory of Green's theorem.
What's the number after that 6 at the very bottom? 6 times.
That's a 5, sorry.
Okay.
I'm having trouble with my pens here. This is a 4. 6 times 5 because it's a 6 by 5 rectangle. 4 times 3 because it's a 4 by 3 inside rectangle. That's twice the area of the outside rectangle minus the area of the inside rectangle. Well, new topic finally. Let's go ahead with this. Surface integral. How about that? We got double integrals to do over plane regions. We got triple integrals over solids. What can we do in normal dimensions where we don't have to go into things we can't imagine anymore? We can use surface integrals. We can integrate over the surface of over a curved surface in space. And this one I won't spend a whole lot of time on. I don't think it's quite as important, but we will use it again in upcoming sessions, so we got to do something with it. Here's the picture. Imagine all of it at once. So there's a second, I should do that. Hard to see some of that though. All right. Suppose I have a surface like this new surface underneath here. And I want to maybe estimate the mass of that surface if it's got a varying density over it. What can I do? Well, I can say approximately it's this little tangent plane here. And if I just took the area of the tangent plane times its average density times an estimate of its density, I can estimate the mass of the surface area by taking the density times the estimated constant density times the area of the plane region and estimate mass of the surface instead. Well, what is the area of this tangent plane? It turns out, we mentioned before, the area of this is a parallelogram, so its area is the length of dr dx cross dr dy. What you do is you take dr dx as the one edge and dr dy is the other edge. Dr dx times delta xj is this thing up here with length delta xj and delta y. This is the run here, delta xj. And then the slope is the rdx, and so you take the run times the slope. I guess I should have length on this. But the run times the slope gives you the Yeah, this vector here is the RDX times delta xj, and this vector here is the RDY times delta yk. And then to find the area of the parallelogram formed by those edges, you take the cross product lengths, and the delta xj and the delta yk come out. So you take the and the result is if you integrate that over region over which the function is defined, but some of those little tangent plane areas get this result. And, what you're doing is taking if you sum over all those plane regions, the plane region times the density function. Think of this as the density function. And then this gives you an estimated mass of the little surface area for the JK. If limit as n goes to infinity, we'll call that the mass of the surface. And then this can be defined to be the surface integral of g of xy is this limit. And you say, well, how do you evaluate that? But this g hat is equal to the integral. So you do the following result. This comes out to be the integral of g of xy times the ds becomes df dx squared plus df. This is the area of the tangent plane right here. If you take that cross product, this is the length. This is the length of the cross product right here. So the length of the cross product times delta x delta y is the area of the parallelogram. And so you're integrating area of the parallelogram, this is infinitesimal parallelogram, times the density at that point. Gives you the mass of the curved surface, if you will. And call that the surface integral. And then there's a special case, if you put integrand g equals 1, we'll call that the area of the surface. So we just put g equals 1. Just like double integral dA is the area of the plane region, double integral ds is the area of the surface. Triple integral dv is the volume. Integrate one to get surface area, special case. So let's try and compute the surface area and the mass, this being surface area and this being mass and g is density. On this surface here, z equals 2x square root of x plus 2 square root 2y over the rectangular region, x going from 0 to 3, y going from 0. Let's try and write that in for you. Evaluate one surface integral. So we can do some of that. The section also talks about doing this in parametric form instead of using this formula. It's harder, and they don't seem to have any problems in back, so I won't get to that tonight. I may not do it at all. That is in the book. So let's turn this back here. So now, surface integral. Surface integral. Find this way, the double integral over sigma, the surface. Of any function g of x, y, ds, that's the notation. This means limit as the number of subregions goes to infinity. So the sum I, little I equals 1 to big I, little j, actually I use jk over there. So, say j, little j equals 1 to big J, little k equals 1 to big K. Of g of any intermediate point x j star k star times the area of the surface element delta s j k, and this is equal to well, it's the area of the tangent plane is integral of df dx, g dx squared plus dg dy squared plus 1. This is a hard, oops. Delta xj, delta y. And this is evaluate xj star y k star. Surface integral is that, so it evaluates as the double integral over the region of g of xy square root g dx squared plus g dy squared plus 1. Thinking of this as ds, say, oh, it's double integral g ds. Does that look like anything familiar? I always have trouble remembering this thing. The way I remember it is this. It's analogous to what we did with arc length. How do we do an arc length parameter? An arc length. We said that the arc length was evaluated by taking the integral from A to B along the one-dimensional line segment. Actually, not the arc length, the mass of a thing. If g of x equals the density function along a wire, I must wrote this is df dx is df dy because f is the surface and I wrote g. Sorry. The surface is z equals f of x y. That is, you have a surface z equals f of x y with a density at each point x y, g of x y. Then you've got this surface integral of g for the surface z equals f of x. And similarly, if g is the density along a curve, y equals f of x. How did you find the mass of a wire along y equals f of x with density equals g of x? You integrated g of x square root df dx squared plus 1 dx, and you call this d little s the arc length, infinitesimal arc length. And you could do that, and this is just analogous. You just add one more derivative in here, and so it's like that one function, one more variable, one more derivative in here, one. So it's analogy to what you did finding the mass of a wire along y equals f of x with density function g of x is to do this with density function g of x y in the plane, and this infinitesimal surface area we call it. Finish my example quick now. Example was this one. Suppose the density is actually is y. I use rho in the example, but and this is a surface given by z equals f of x, y is this one. 2x square root x plus 2 square root 2y. So that'll be the surface that you're integrating this density. We're trying to find the mass of it. And it's over the rectangle 0 to 3, 0 to 1. Then you just apply this formula, maybe call it 2. So apply equation 2, integral y ds the sigma is the double integral over the rectangle below where x goes from 0 to 3, y goes from 0 to 1. G of x, y is y. And then square root of, this is your f of x, y. You've got the f dx then is 2x sub 3 has derivative is 3x to the 1/2. Plus, partial with respect to y is 2 square root 2. D, y, dx. And now we can evaluate this as integral 0 to 3. And,
Plus 1 square root.
oh, plus 1, yeah, thank you. Plus 1, y dx, yeah. Square root of 9x plus 8 on 9. Good problem. So you pull the square root of 9 out and call it 3 times the integral from 0 to 3, integral from 0 to 1 of y square root x plus 1 y dx. And now you notice since it's a product of a function of y times a function of x over constant endpoints, you can break it up to a product of integrals. Integral from 3 of square root x plus 1 dx. Integral from 0 to 1 y dy. Maybe I'll just leave that. Make a substitution u equal x plus 1. So it comes out to be 7, I guess. So I'll leave out the steps since we're out of time. Just say that comes out to be 7. Good. Let me give you the problems to look at then. I think I'll wait on the surface integrals to look in the handout problems, numbers 1 through 10. 5 of those at the end. 4.2.3. Problems 1 to 10. We should be able to do all of those. Those include a bunch of problems on line integrals, on Green's theorem. I think that's it. No surface integrals in there. Yeah, 4.3.2 is what it is. Hey, I found a good pen right at the end. How about that? 1 to 10.
No, from D2L.
They're already on D2L, yeah. Also, if you want 15.5 on surface integrals, we can look at this one. Yeah, 1, 3, and 5 are like this one we just did. That'll be it. That might be more than we want to do for Wednesday, but. Other than that,